In a dark, quiet studio on the world map, there is one place that always looks empty and peaceful. A white spot at the bottom, an icy circle we're used to not thinking about. Antarctica. For most people, it's just a cold end of the world where expeditions sometimes go and where penguins live. But for scientists, Antarctica is not a background. It's a time bomb in 3 directions at once: climate, ocean, and invisible life. In a dark, quiet studio on the world map, there is one place that always looks empty and peaceful. A white spot at the bottom, an icy circle we're used to not thinking about. Antarctica. For most people, it's just a cold end of the world where expeditions sometimes go and where penguins live. But for scientists, Antarctica is not a background. It's a time bomb in 3 directions at once: climate, ocean, and invisible life under kilometers of ice. Today, when you go to sleep, this continent will continue to crack, melt, and shift, centimeter by centimeter. Somewhere under 3 kilometers of ice, liquid water is flowing right now. Ancient microbes are working. Gases are being released that don't rise up only because the cold holds them. Somewhere, warm ocean water is already entering under glaciers for tens of kilometers deep, undermining them from below. Somewhere, the giant Doomsday Glacier is slowly crawling toward the ocean, holding back a whole region of ice behind it, which in the future could raise sea level by meters. This video won't be about fantasies and Hollywood scenarios. We will talk about what is already happening, about why serious climatologists and glaciologists today are much more nervous looking at Antarctica than thinking about the Mariana Trench, about what hides under the ice: subglacial lakes, unknown ecosystems, microbes that lived in isolation for thousands of years, about how one glacier is capable of changing the map of coastlines, and about why science increasingly uses the word point of no return when speaking about this continent. If you are interested not just in where penguins live, but what can really affect the cities we live in, the seas we vacation by, and the climate we are used to, subscribe to our channel. Here we analyze stories about places almost no one reaches, but on which the future of everyone else depends. Like this video? Get comfortable. Wrap yourself in a blanket. We are heading to Antarctica, to where the ice seems eternal, but it is precisely what is feared most. Antarctica is not just a lot of snow at the bottom of the map. Under the ice, there lies a real continent, almost the size of the US and Mexico combined, with mountains, valleys, depressions, ancient rocks. On top, all this is covered by a gigantic ice sheet. In places, the ice there reaches 3 to 4 kilometers in thickness. That is, above the rock, above solid ground, lies a layer of frozen water thicker than many mountain ranges. Locked in this ice is such an amount of water that if it melts entirely, the global sea level will rise by approximately 58 meters. This figure isn't for beauty. 58 meters means vanished coastal areas, flooded ports, airports, embankments, whole cities and countries with low shores. Many familiar outlines of continents will simply cease to exist in the form we know them. For a long time, it was thought that this ice sheet was very slow and stable. In textbooks, Antarctica looked like something eternal that almost doesn't change. But modern satellite measurements show a completely different picture. In some regions, ice has begun losing mass several times faster than expected. Thickness decreases, glaciers retreat, and instead of eternal freeze, we see a system that has already been set in motion. And it's not all of Antarctica at once behaving restlessly, but its western part. That is exactly where the object sits to which scientists gave the unofficial nickname Doomsday Glacier. On the map, it is called Thwaites Glacier. It is a huge river of ice in West Antarctica sliding into the Amundsen Sea.
Thwaites itself is already losing tens of billions of tons of ice per year today and contributes a noticeable share to current sea level rise. But the main problem isn't in it alone, but in the fact that it stands first in line. Imagine a bookshelf where one heavy book supports another. While it stands in place, everything is stable.
But if you slightly move the end volume, the whole stack can collapse. Thwaites Glacier is exactly such an end book for a large chunk of the West Antarctic ice sheet. It rests on an underwater ridge and partially holds back other masses of ice behind it. Today, Thwaites has an ice tongue, a shelf that floats on water and sort of breaks the movement of ice from land. Under the action of warm ocean water, this shelf cracks and thins from below. When it finally loses strength, ice from the continent will be able to slide into the ocean much faster. Thwaites alone in such a case is capable of adding more than half a meter to sea level. But it also opens the way for other glaciers behind it, and then we will be talking about meters over the coming centuries. But if the threat came only from warm water outside, the situation would be half the trouble. The real shock for the scientific world happened quite recently, in 2017, when researchers looked under the West Antarctic ice sheet using radar. We are used to thinking of this continent as an icy desert, but it turned out that right under the feet of Thwaites Glacier and its neighbors hides a real hell. Scientists discovered 91 new volcanoes there that no one knew about before. If we add the already known ones to them, it turns out West Antarctica sits on one of the largest volcanic systems on the planet. It can rival the Great East African Rift. Imagine almost 1,500 volcanoes hidden under kilometers of ice, many of which are active and release heat. This changes the whole equation. Antarctica is not just ice on rock, it is ice on a hot plate. The geothermal flux, heat coming from the depths of the Earth, in this region is anomalously high. Volcanoes don't necessarily have to erupt with fountains of lava to be dangerous. It is enough for them just to breathe heat. This heat melts ice at the very base, where it touches the rock. In a normal situation, a glacier freezes to the bottom and holds onto it like a brake. But when volcanic heat works from below, a layer of water forms. Water works as an ideal lubricant. A gigantic mass of ice stops gripping the ground and begins to slide. It's like putting a heavy wardrobe, not on a carpet, but on wet ice. It will slide from the slightest push. And this scares glaciologists most of all. If one of these subglacial volcanoes enters an active phase of eruption, it won't punch through the 3-kilometer thickness of ice. We won't see smoke and fire, but it will create gigantic volumes of meltwater below. This water will lift the glacier like a hydraulic jack and sharply accelerate it sliding into the ocean. We are talking about a system where fire and ice work in tandem, and this factor of heating from below was not accounted for in climate models for a long time at all. There are visible proofs of this power too. Mount Erebus, the southernmost active volcano on Earth, rising above the ice. It constantly smokes, releasing gases and, surprisingly, microscopic gold crystals. But Erebus is only the tip of the iceberg, a guard visible to all. A real army of volcanoes sleeps below, in darkness, under the weight of billions of tons of ice. And the question, will they wake up, is not a question of curiosity, it's a question of how quickly the world map will lose its familiar shores. West Antarctica is generally considered more unstable than East. A significant part of its glaciers rests not on land, but on the seabed below sea level. This is called a marine ice sheet. If warm water gets under it, the ice loses support and begins sliding into the ocean. Therefore, scientists look at the Amundsen Sea region, at Thwaites and neighboring glaciers, as the weak link of the entire system.
Cracks, acceleration of ice movement, and retreat of the line where the glacier is pressed to the bottom are already being recorded there. It is in these numbers and maps that the very alarming question is born. Are we observing fluctuations normal for Antarctica, or the beginning of a large, long, and already irreversible shift? Climatologists increasingly say that part of the changes in West Antarctica seems to have already passed the point where everything can be returned back by a simple "we stop emissions and everything freezes." When people say ice is melting, most imagine a bright sun warming from above. In Antarctica, the main threat isn't from there at all. The most dangerous thing now is happening from below, where no one sees it. Under many coastal glaciers, in the same Amundsen Sea where Thwaite stands, warm ocean water is working quietly. Antarctic glaciers have a floating part, shelves. These are like huge ice bridges extending from land into the ocean and resting half on water. While this bridge is intact, it breaks the ice lying on the continent behind. But from below, relatively warmer water of deep currents creeps up to it. It isn't warm by human sensation, it's still only a few degrees above zero there. But for ice, it's the difference between standing and melting. Satellite and subglacial measurements show that such water is already entering under shelves for tens of kilometers deep, right up to those lines where ice is still pressed to the continent's bottom. There, in total darkness, ice melts from below, becomes thinner, cracks. When it loses thickness and strength, huge fissures appear in it, and at some moment, the shelf simply breaks into pieces. Each such lost slab is like a released break. After its collapse, ice from land begins sliding into the ocean faster. The most unpleasant thing for scientists here is that this process is difficult to turn off. Air warming can be relatively quickly slowed down if emissions are reduced, but the ocean is a huge heat machine with huge inertia. Even if tomorrow the world miraculously stops burning fuel, that warm water which has already reached Antarctic shores and under shelves won't disappear. It will circulate around the continent for many more decades or even centuries, continuing to eat away at the ice from below. There is one more nuance glaciologists often talk about. When a shelf thins and loses support, the line where ice touches the bottom, it's called the grounding line, retreats further and further inland. And there, the bottom is often even deeper. A retrograde slope results. Ice loses support, slides off, even more water enters under it, and the process accelerates itself. At some moment, this turns into not simply melting, but into a sustained collapse, like a slow but inevitable landslide of ice. This is exactly why many scientists say West Antarctica may continue collapsing, even with relatively modest further warming. Here, it's no longer enough simply to cool the air. Time is needed for the ocean to cool. And judging by the rates, we have less time than we would like. While we argue about degrees on the surface, under kilometers of ice, a quiet undermining is going on, and Antarctica is literally losing its foundation from within. When you look at Antarctica from above, it seems like just a continuous white field of ice. But if you mentally slice off this ice and look under it, the picture becomes completely different. Under some sections of the 3-kilometer ice sheet hide entire systems of rivers and lakes, the existence of which people didn't even suspect until the second half of the 20th century. Scientists now estimate under Antarctic ice are several hundred subglacial lakes and interconnected water channels. These are not warm lakes in our usual sense, but pockets of liquid water sandwiched between solid bottom and heavy ice lid.
Water there doesn't freeze not because it's warm, but because pressure is enormous and a little heat comes from below from the Earth's interior. Ice presses from above like the lid of a gigantic pot, and rocks from below heat slightly. As a result, a thin layer of water is obtained that can exist in such conditions for millennia. The most famous of such lakes are Whillans and Mercer. To reach them, expeditions had to drill more than 800 to 1,000 meters of ice, and do so in a way not to introduce microbes from the surface. The entire drilling system is sterile, like in an operating room. When finally the first liters of water are obtained, they are literally from another world. This water hasn't seen the sky for thousands of years. What was found in these samples very quickly removed the illusion that everything under the ice is dead. In the water and sediments of Lakes Whillans and Mercer, dozens and hundreds of microbe species were discovered, bacteria and archaea living without sunlight. There are no algae, no familiar photosynthesizing life. These communities feed not on light, but on chemistry. They oxidize iron, sulfur, ammonia, use compounds washed out of rocks and brought by current from below. Effectively, they live on the energy of the reaction between stone and water. The age of these ecosystems is a separate reason why scientists get goosebumps. According to estimates, part of such lakes was isolated from the surface for tens of thousands of years, and some large systems under the ice of East Antarctica could have been in isolation since times when there were no cities and agriculture on the planet yet. During all this time, neither leaves, nor rain, nor ordinary microorganisms from the ocean got there. Life there developed by its own rules, in its own preservation jar. Especially interesting is that microbes found a way to use even minimal energy sources. In sediments at the bottom of these lakes, traces of organisms were found that slowly process organics brought there by glaciers thousands of years ago. Other groups feed on products of rock decomposition. Their growth rate is so small that a separate cell might divide once in tens or hundreds of years, but this is enough to sustain a whole community. For scientists, these subglacial ecosystems are simultaneously a window into Earth's past and a model of what life might look like on other icy worlds like the moons of Jupiter and Saturn. This is proof that life can exist where there is no sunlight, where there is only stone, water, pressure, and very slow chemical reactions. And all this right under our feet, under the multi-kilometer ice of Antarctica, which we recently thought of as a dead shield. The next logical step is to talk about what scientists fear most in these hidden worlds, about microbes and viruses that haven't contacted anyone for thousands of years and can now enter the big ocean along with melting ice. When we say ice, most people think of something clean and sterile. But for microbiologists, Antarctica is not a sterile refrigerator, but a huge archive of life. Ice, snow, subglacial lakes, frozen sediments, all this together forms what scientists call the cryosphere. And in recent years it became clear, inside this refrigerator, a whole invisible zoo is hidden. In samples from Antarctic ice and subglacial lakes, thousands of different types of microbes are found: bacteria, archaea, fungi, and viruses. Many of them resemble nothing described in ordinary soils or oceans. When scientists compare their DNA with known databases, a significant part of sequences falls into the category unknown what to attribute. This means we don't even roughly understand how these organisms live and what functions they perform. A separate topic is viruses. In ordinary ecosystems, viruses play an important role. They infect bacteria, control population numbers, transfer genes between organisms.
In Antarctic ice and subglacial waters, whole groups of viruses are found which, judging by genes, have never met modern surface ecosystems. This doesn't mean viruses of the apocalypse are hiding there, but it means we are dealing with a huge reservoir of biological diversity about which almost nothing is known. Scientists are cautious in formulations now. Most don't speak about a direct threat of ancient epidemics about to break free. The main fear is different. When ice melts, when subglacial lakes begin connecting with the ocean, all these microbial communities and viruses get into completely different conditions. They might not survive, or they might integrate into existing chains, change the cycle of carbon, nitrogen, methane. Some might start infecting local bacteria and algae, changing the work of local ecosystems. Add to this that many of these microbes live off chemical reactions with rocks and gases. They, for example, know how to process methane, oxidize iron and sulfur. If conditions change, their role in gas balance might change too. Someone will eat more greenhouse gases, and someone, on the contrary, will start releasing them. For climatologists, Antarctica in this sense is a black box. Inside it are working biological processes difficult to account for in models so far. Therefore, the cryosphere is increasingly described as a reservoir of the unknown. Organisms and viruses are hidden there with which our modern biosphere either hasn't encountered yet or lost contact long ago. And as ice changes, this archive begins to open little by little, not according to our schedule, but according to laws of physics and climate. The next step is to look at yet another element of this hidden world, gases under the ice, primarily methane, and why scientists closely watch possible breaths of Antarctica. Antarctica scares scientists not only with ice that melts, but also with what is under that ice. The matter isn't only water, but also gases accumulated there. One of the main ones is methane. This is a powerful greenhouse gas, several times stronger than carbon dioxide in influence on warming, especially in a short time span. Under the Antarctic shield, zones have already been found where hot flows rich in methane come from the depths. Where heat from deep rocks and ice pressure meet water, so-called methane hydrates can form. This is like ice in whose structure gas is locked. Such gas ices are known on the seabed all over the world, but in Antarctica they're hidden even deeper, under kilometers of ordinary ice and sediments. In normal conditions, this methane is in no hurry to go anywhere. It either remains bound in hydrates or is slowly processed by local microbes that know how to eat it, turning it into other substances. But the system holds on a balance of pressure, temperature, and ice thickness. If one of these parameters changes sharply, the storage can become less stable. When ice thins, pressure from above drops. When warmer water reaches the glacier base, soil and sediments heat up. At some moment, part of hydrates can start melting and dissolved gas releasing into pores, cracks, into water. Part of this methane will indeed be intercepted by microbes, especially if the process goes slowly. Microbial communities in Antarctica have already shown they know how to process greenhouse gases in extreme conditions. But if melting goes faster than the microbial disposal service manages to react, excess gas can go further, first into the ocean, then into the atmosphere. For climate, this is an unpleasant scenario, a natural source of greenhouse gas that turns on by itself as a response to already begun warming. Such an effect is called a positive feedback. The warmer it is, the more methane is released. The more methane, the warmer it becomes still. Antarctica, in this sense, is a potential player long underestimated.
And that means higher risk of accidents, spills, conflicts. All this is superimposed on an already unstable natural system. Antarctica, even without us, is now experiencing a period of rapid changes. Glaciers are melting, currents changing, no wind pelts rising. In such a situation, any additional stress, from local pollution to political confrontation over resources, makes the continent's future even more unpredictable. Scientists increasingly say that Antarctica needs not only to be studied, but very carefully not touched unnecessarily, because we are now interfering in a system whose operation consequences we don't fully understand. Sometimes, to understand how dangerous something is, one needs to compare it with what already scares us. The Mariana Trench is an ideal example. We are used to the image of the scariest point on the planet. 11 kilometers of darkness, monstrous pressure, strange creatures, and a plastic bag on the bottom. Toxins, microplastic, radioactive substances, creatures living on chemistry rather than sunlight were found there. This place looks like an alien planet, yet scientists look at it rather as a mirror than a threat. The Mariana Trench shows us consequences.
Everything humanity dumped into the ocean eventually ends up there, in sediments, in bodies of deep-sea animals, in the form of a garbage layer on the very bottom. But at the same time, the trench itself does nothing to the world above. It doesn't change sea level, doesn't move continents, doesn't turn on new gas storages. It is the final pit where what we have already done flows down. Antarctica is a different story. It is not a passive bottom, but a huge lever connected to the whole planet. If the Mariana Trench is a grave for our garbage, then Antarctica is a mechanism capable of changing living conditions on coasts, restructuring climate zones, affecting the work of ocean currents and even biological cycles through the release of gases and microbes from under the ice. Imagine two buttons. One is far at the bottom of the trench. It cannot be pressed, it is already pressed in by pressure, and everything happening there almost doesn't get out. The other is Antarctica. It is connected by cables to all oceans, to winds, to air temperature. Any change in it echoes throughout the world. Shelf melts, glaciers accelerate. Glaciers accelerate, sea level rises. Ice changes, currents change. Currents change, familiar climate zones restructure. Which sounds scarier? A place where our mistakes already lie, or a place where it is still being decided what the consequences of these mistakes will be? This is exactly why many scientists who spent years on deep-sea trenches say today they are more worried about ice than the abyss. Antarctica scares scientists not because it's cold and far, but because three types of risk converged in one place at once. The first is obvious: ice. If Antarctica continues losing mass as now, global sea level will rise not only from thermal expansion of water, but from real addition of meltwater. Centimeters are already being recorded. Tens of centimeters and meters are a question of time and scenarios, not fiction. For coastal cities, this isn't a pretty picture but flooded embankments, infrastructure going underwater, and constant storm surges where there weren't any before. The second layer of fear is the ocean itself. Antarctica is like a huge cold anchor helping control global currents. Ice there affects salinity and density of water, and that means the work of the conveyor belt of ocean currents transferring heat around the planet. If this anchor starts behaving differently, winds, storms, rainy seasons, and droughts will start restructuring in places that seem very far from ice. What today looks like somewhere there a glacier is melting, in decades can turn into a different summer over the Mediterranean Sea, different winters in Europe, or a different frequency of extreme weather events.
It is the world under ice. Microbes, viruses, methane, other gases isolated for thousands of years in the cold archive of Antarctica. As ice changes, this archive begins to open, not in the dramatic style of movies about ancient viruses, but in a real, much more complex one. New microbial communities get into the ocean, come into contact with the modern biosphere, and change paths of organic decomposition and greenhouse gas cycle. Part of gas will be processed by microbes, part might escape into the atmosphere. These processes are still poorly accounted for in models, and this is exactly what irritates and worries researchers most. A huge chunk of the system we describe very roughly so far. Altogether makes Antarctica not a distant picture with penguins, but the main unknown parameter in the equation of humanity's future. We know for sure this continent is already changing. We know that partially processes, especially in West Antarctica, might be irreversible on a human timescale. We don't fully know only the speed and exact consequences. Will it be a smooth sea level rise and gradual climate restructuring, or a series of sharp steps when over 1-2 centuries whole regions find themselves in new conditions? Antarctica is not a monster that will climb out tomorrow. Not an instant end of the world.
It is a huge, heavy mechanism that has already been set in motion and will determine what coasts, storms, and familiar seasons will look like for our children and grandchildren. The white spot on the map turned out not empty, but perhaps the most important and most nervous place on the planet. If you are interested in such stories, not only about monsters from the depths, but about real, quiet threats changing our world, subscribe to the channel. Here we talk about those places you are unlikely to visit personally, but on which the cities you live in depend. Like if Antarctica after this video stopped being just a white circle at the bottom of the map and turned into a living, dangerous, and not fully understood continent. The ocean and ice keep their secrets, and we will continue uncovering them together with you.